Hello ladies and gentlemen, thank you for watching this video and welcome on my channel. In a previous video about the flat earth, I calculated, among other things, how fast the sun moves around the North Pole. Today I will use planar trigonometry to determine the height of the sun above the Earth's surface. Probably you have already seen geodesists or surveyors. These guys measure landscapes and buildings. You can determine the height of a building, for example, from the ground. How do you do that? First, they measure the distance from their position to the base of the building. Nowadays this is done with laser. Then they aim the theodolite at the top of the building, determine the angle at which they see it, and can determine the height from the distance and the angle. Let's take a look at this illustration. The building is on the right. A is the base of the building and C is the top. The surveyor stands at point B and first determines the distance C and then the angle beta. Here alpha is by definition a right angle. For a right triangle the following applies. The tangent of beta is equal to the ratio between the opposite side B and the adjacent side C. We have to find the height B. So we multiply both sides with C and get height B is equal to tangent beta multiplied by the distance C. Don't be afraid of the tangent. A scientific pocket calculator that can calculate this function can be opened in every computer. For example, if the distance to the house is 100 meters and we see the top of the house at an angle of 15 degrees, then we get height B is tangent of 15 multiplied by 100 meters, or 0.26 multiplied by 100 meters is 26.8 meters. On the other hand, if we see the upper edge of the neighboring house at an angle of 30 degrees, we calculate the height to 57.7 meters. If people stand 200 or 50 meters away from the house instead of 100 meters, they will of course see it from a different angle. In the same way we can determine the height of the sun above the flat earth. We only need the distance from us to the point above which the sun is in zenith, it is perpendicular, and the angle at which we can see the sun at noon. Let's take Mainz as an example, which is at 50 degrees north. Around the 21st of September and the 21st of March, the sun is at its zenith over the equator at noon. In Mainz we see the sun at noon at an angle of 40 degrees. The distance of the 50th parallel to the equator is 5,555 kilometers. We put all this into the above formula from the tangents theorem. Height B is tangent beta multiplied by distance C, and we get tangent 40 degrees multiplied by 5,555 kilometers, or 0.839 multiplied by 5,555, and this equals to 4,661 kilometers. How does this altitude change with the season? If you are wondering about this question, it should be said that the speed of the sun over the flat earth also changes with the season, because of the Tropic of Capricorn is much longer on the flat earth than the equator or even the Tropic of Cancer, and so the sun must move faster on the flat earth in northern winter than in northern summer. So why shouldn't the height of the sun change too? We have two other important dates we can use for calculation. At the solstice on December 21st, when the sun is in the zenith over the Tropic of Capricorn in 23.5 degrees south, the sun in Mainz will be at 16.5 degrees above the horizon at noon. The tangent of 16.5 degrees is 0.296. The distance from Mainz to the tropic is 8,158.5 kilometers, and we get the height of the sun above the earth on December 21st to 2,417 kilometers. And the solstice on June 21st, with the sun is in the center of the Tropic of Cancer in 23.5 degrees north. The sun in Mainz will be 63.5 degrees above the horizon at noon. And we get, after the computation, the height of the sun is 5,900 kilometers. We get from the observations in Mainz that the sun is 2,417 kilometers above the Tropic of Capricorn at the beginning of winter, 4,661 kilometers above the equator at the beginning of spring, and 5,900 kilometers above the Tropic of Cancer at the beginning of summer. If you imagine the flat Earth being covered by a kind of dome, which is highest towards the North Pole and slopes down to the edges, and if you imagine the sun moving along this dome, then you may see this as explanation for the different heights. Of course, proper scientific work also includes looking at other constellations. We will therefore now calculate the heights for the sun for different places on Earth at the time of the equinox on March 21st and September 21st. Besides Mainz at 15 degrees north, we take Oslo 60 degrees north, New York 40 degrees north, and Suez 30 degrees north. In Oslo, the sun is 30 degrees above the horizon at noon. The tangent of 30 degrees is 0.577. The distance from Oslo to the equator is 6,666 kilometers, and the height of the sun is 3,849 kilometers. In Mainz, as we have seen before, the height of the sun is 4,661 kilometers. In New York, the sun is 50 degrees above the horizon at noon. The tangent of 50 degrees is 1.192. The distance from New York to the equator is 4,444 kilometers, and the height of the sun computes to 5,296 kilometers. In Suez, 30 degrees north, the sun is 60 degrees above the horizon at noon. The tangent of 60 degrees is 1.732. The distance from Suez to the equator is 3,333 kilometers. So the height of the sun is 5,773 kilometers. Surprisingly, these calculations, with the help of planar trigonometry, result in different heights of the sun above the flat Earth for the same date at different locations. Assuming the Earth is flat, I have no explanation for this. Perhaps a viewer is so well versed in the theory of the flat Earth that he has an explanation for it and can explain it to me. Otherwise, I have to assume that the Earth is a sphere after all, because the angles at which we see the sun in the different places exactly match a huge light source that is far away and whose rays of light hit the ball-shaped Earth in parallel. Thanks for watching and have a nice day, and I hope I will see you again in one of my next videos. Bye bye.